Okay, so air. First part of the air is you need to know the composition of clean air. So I'm pretty sure you've seen this diagram before. Can anybody tell me, can anyone say that they haven't seen this diagram before or this composition before? No? So I'm guessing everybody has seen this before. Not necessarily the pie diagram, not necessarily the pie chart, but I'm sure at some level, like probably in grade 6, grade 7, maybe grade 8, somewhere around there, you probably did the composition of air. And maybe you even did it in geography. Maybe you didn't even do it in science. Cool. So when we talk about air, we literally mean the stuff that's around us, like right now, the stuff that you literally breathing in as we're talking. So everything that you can't see, that's between you and the walls of your house, that's the air that we're talking about. And it's not empty space. It's not like there's nothing there. We obviously know that there's gases that are there. And those gases are 78% nitrogen and 21% oxygen, approximately. And then other gases, including argon and carbon dioxide, as well as other noble gases, and then a bit of water vapor as well. And then recall that in terms of reactivity, combustion only involves oxygen. So if you light a candle, for example, it's going to react with the oxygen in the air, but the nitrogen is relatively unreactive. It's not really doing much. It's just kind of sitting there. And then for interest's sake, right at the bottom, it's not in the syllabus, just for interest's sake, the composition of air does change depending on where you are in the world. But when I say change, I don't mean like 78 to 60. I mean like 78 could change from 78 to 78.5. I'm saying that it's not identical everywhere you go around the world. So for example, if you went to the Amazon rainforest, would you expect oxygen level to be higher or lower?
Higher.
Higher, and the reason is?
Photosynthesis.
There you go. Photosynthesis produces oxygen. So it's likely that you'll find a higher concentration of oxygen there. However, it's not significantly higher. It's maybe like 1 or 2% higher. That's the interesting part. The interesting thing about the air around us is that the composition is fairly consistent wherever we go. Cool. And then obviously there's a bit of water vapor. And we know that here, especially in Walvis and Swakop, we have a lot of humidity in the air. So the air often feels moist, it feels wet. So our water composition would obviously be a little bit higher than most places. So if you go to Windhoek, the humidity is almost 0. It's as dry can be, which means their water level is probably even lower than average. Cool. Anyone got any questions on that? No, we good? Okay, good stuff. So common pollutants in air. The 3 common pollutants you have to know are carbon monoxide, sulfur dioxide, and then oxides of nitrogen. So carbon monoxide, which is not carbon dioxide, they're not the same thing. Carbon monoxide is formed from the incomplete combustion of fuels. So for example, if you're burning a candle and some of it doesn't burn completely with oxygen, you're going to form mostly carbon dioxide, but you're also going to form a tiny amount of carbon monoxide. Tiny amount, but it will be produced if there's incomplete combustion. Cool. And the adverse effects of this is it's extremely poisonous. Carbon dioxide is mildly toxic. Like you can breathe in carbon dioxide and you'll be fine. But if you breathe in carbon monoxide in high concentrations, it can kill you like almost instantly. Does anyone know why? Who does biology? Who can tell me why?
It's going to steal your oxygen because it wants to complete carbon dioxide, I think.
Correct. So in terms of your hemoglobin, your oxygen carrying molecules, it's going to sit in the place where the oxygen wants to be. So it's going to attach itself to the hemoglobin molecule. And that process is almost irreversible, meaning we can't get rid of it. So once it's on the hemoglobin, it's stuck. And now your body doesn't have, or your blood doesn't have the capacity to carry oxygen anymore. So carbon monoxide poisoning is extremely dangerous. Whereas we can breathe in carbon dioxide, in fact, we do breathe in carbon dioxide because we sometimes inhale the air that we breathe out. So that's not poisonous. Cool. And then sulfur dioxide, combustion of fossil fuels containing sulfur. So for example, coal and diesel, when you think of a lump of coal, you think of like a really large black solid. However, that's not all carbon. It's like 99% carbon, and it has a bit of extra, whatever, it's sulfur, nitrogen, phosphorus, whatever. But the tiny amount of sulfur that's inside the coal, when it's combusted, produces sulfur dioxide. So it produces the SO2. And the problem with this is that the SO2 dissolves in water and it creates an acidic solution. So it's not quite sulfuric acid. It's a milder version of sulfuric acid, and it dissolves in the atmosphere and it comes down as what we call acid rain. So has anyone heard of acid rain before?
Yes,
Yes. So it's an interesting concept because it literally rains acid. So when we talk about acids and bases, we're talking about things that are that have a low pH. And this is bad because what do acids react with? If you think back to the acids topic,
with metals,
Metal.
bases, and carbon.
correct.
And carbon.
Metal and carbonates, correct. So if you think about a metal building or a structure inside a building that's made of metal, if this rains down on the building that's composed of metal, it's going to react with that metal, and it's basically going to eat away at it. And in certain places, they make buildings out of limestone or statues or whatever. And limestone is basically calcium carbonate, and carbonates react with acids. We know that as well. So you'll find that buildings get quickly deteriorated when there's acid rain problems. Has anyone ever seen images of this? Actually, this note is the one that I'm not done with. So I will add pictures of this to the note for you. But has anyone ever seen this before?
No.
So I've never seen it in person, but I'll show you a couple of photos later. You can see that the buildings look like they've been almost eaten away. They start corroding. Cool. And then the last one you have to know is the oxides of nitrogen. Now, remember what we said is that the nitrogen is mostly unreactive. It's in the air and it's sitting around us all the time and it's practically doing nothing. However, when you apply a lot of heat and a lot of pressure, it can react with the oxygen in the air. And a good example of this is when the combustion takes place inside an engine, because an engine produces a large amount of heat, and it produces enough heat that it actually allows the nitrogen to react. So in engines and in high temperature furnaces, the nitrogen in the air actually does combust with the oxygen to produce nitrogen oxides, nitrous oxides or whatever they call. And then it has similar adverse effects because it also dissolves in water to give acid rain, but it also produces breathing problems, especially for people suffering with asthma. Cool. Where else do you see a lot of high heat and temperature in the environment? Where can you think of a situation where there's a lot of high heat and temperature that could occur in nature? Where do you think this could also occur in nature where there's a lot of high heat and temperature?
Volcanoes.
Ah, there we go. Perfect. Volcanic eruptions. So if you think about a volcanic eruption, if it's super hot, it's possible that it can cause the reaction of the nitrogen to occur. Cool. And then another interesting one that you might not have thought about is lightning. Lightning is actually a super high energy beam of electricity, and that electricity has enough energy to cause the nitrogen to react. So when there's lightning strikes, we actually do produce tiny amounts of nitrogen dioxide or nitrogen monoxide in the atmosphere. So it's quite an interesting thing. Cool. Any questions on that?
No, sir.
No? So if you look at what the syllabus asks you, it basically says in point 3, 3, 6, and 7. No, I'm lying to you. In 2, 3, and 6, we've basically summarized point 2, point 3, and point 6 in the table. Point 2 is naming the common pollutants. Point 3 is where do they come from? And point 6 is what adverse effects do they have? So if you look in the top left-hand corner of the slide, you'll see that it's 2 plus 3 plus 6 common pollutants of air. What are they? What are their sources? And why are they bad? Cool. Rusting. So we live in Walvis and Swakop, some of us. You see rust every day, don't you?
Mhm.
Yeah, so somewhere around the house, if you look at one of your doorknobs, or if you look at something in your kitchen, or if you look at something in your garage, or if you look at your car, if it's been chipped, you're going to see rust everywhere. And the reason is because we have a lot of moisture content in the air. And one of the best conditions for rusting is a high concentration of water. So in order for rusting to occur, we need water and we need oxygen. And like we said earlier, in Walvis Bay, we have high humidity, which means we have high water concentration in the air. Cool. So the question is, if we want to stop rusting, we have to eliminate either the water or we have to eliminate the oxygen. Cool. And one way of eliminating the oxygen is by literally putting a layer over it, correct? So you could paint it or you could put oil over it. Cool. So you can prevent it from that, like that. Cool. And then the less obvious one is to try and remove the water. And again, you could put a layer over it, or you could get chemicals that absorb the water. So for example, calcium chloride is a good absorber of water, and what it'll do is absorb the moisture in the air, and it won't allow that water to come into contact with the metal so that it won't rust. Cool. And then an interesting thing is that if you boil water, you actually remove the oxygen from the water. So boiling water deoxygenates the water because the oxygen has such a low boiling point. When you boil it, it bubbles out and it becomes a gas in the atmosphere. So if you look at this middle test tube here, we've boiled the water so that there's no oxygen, and then we put a layer of oil on top so that no more oxygen can come in. And that nail there won't rust. Cool. Any questions?
So how's it water if you remove the oxygen?
Very good question. So we're not actually removing the oxygen from the H2O. It's a mixture of water and oxygen. So the oxygen is actually dissolved into the water. So it's not that, yeah, say that.
So you're removing the excess, like the extra oxygen.
Correct, 100%. So I think I can annotate here. You're thinking of H2O as being, let me just change the color. You're thinking of H2O as being H and then 2 and O. What we're saying is that it's that, and inside the water, we also have dissolved oxygen. So it's not chemically bonded to the water. It's oxygen dissolved in water.
Okay.
So when you think back to C3, atoms, compounds, and mixtures, water is a compound, which is H2O. It's chemically bonded together, but we can add things to the water to make it a mixture. And in this case, it's a mixture of water and oxygen.
Okay.
But like we can separate any mixtures, we can separate the water from the oxygen, and we can take out the excess oxygen. So if that's not clear, I'll explain it again at another stage. I'll make a note of that. That's an interesting concept. Cool. So preventing rusting, you can paint it or you can grease it. What's the problem with painting?
It can peel.
It can peel off, correct. So you know that sometimes if your parents own a car, or if you've ever been in someone's car that's very protective, they don't like bumps and scratches. And the reason you don't like bumps and scratches is because once you remove the paint, it exposes the metal underneath. So when somebody says, don't like slam my door against the wall, or be careful when you get in, don't scratch the whatever, it's because they know that if you start scratching the paint off, it's going to start rusting underneath. And once it starts, it doesn't stop. That's the problem. Cool. And then for those of you that have a bicycle, for example, you know that you put grease or you oil your chain or you put some kind of lubricant on top of the chain, and that prevents the rusting. But what's the problem with that?
You need to reapply it.
You do. You need to constantly reapply it. So especially when there's a lot of friction and that surface is being used a lot, the grease or the layer is going to constantly rub off. So you have to constantly reapply it. Cool. This is the slide that I still need to fill in, reducing sulfur dioxide emissions. So I need to find a nice little picture or something to add here and write a few sentences. But basically the note is done except for this. Cool. This last topic is only for extended. I forgot to write it at the top here, but it's extended only. The core guys, you can listen because it's interesting, but you don't need to know any of this. In fact, some of you might know more about this than I do. So I'm thinking of John in particular. He likes cars and things. So John, do you know anything about exhausts?
No, not really, sir. Just
Okay,
know
cool.
that
But
carbon
you like
monoxide
that?
comes out.
Pardon, say that again.
I only know that carbon monoxide comes out the back.
Correct. So at the back of your car, you've got the exhaust pipe where all the gases come out, but just before the exhaust, you get this large tank. If you see a car and if it doesn't look suspicious, go and look under the car and see if you can see this. It's got this huge tank that's just before the exhaust pipe. And that tank there is not empty. It's not just an empty drum. It's actually got a catalytic surface on the inside. So remember when we did rates of reactions, we talked about catalysts, more or less?
Yeah.
Yeah. So this is a catalytic surface. In other words, it's a surface that acts as a catalyst, but it doesn't take part in the reaction. In other words, we don't use up the catalyst. It's constantly there. And what that does is it takes the harmful gases, the carbon monoxide and the carbon monoxide and the nitrogen monoxide, and it converts it to carbon dioxide, oxygen, and nitrogen. And those gases are like 90% less dangerous than the other two that would have otherwise come out. Cool. So as a summary, you can say a catalytic converter is connected to the exhaust pipe on a vehicle. When fuel is combusted, two things happen. You get incomplete combustion of fuel, which produces the carbon monoxide. So we talked about that earlier. When something undergoes incomplete combustion, you get carbon monoxide. And then you get the combustion of the nitrogen, producing nitrogen monoxide. And again, we said this happens inside the engine because of the high heat and pressure. And then we said that CO and NO are harmful to humans and the environment, as previously stated. And what the catalytic converter does is it takes those harmful chemicals and turns it into carbon dioxide, nitrogen, and I forgot to add there oxygen as well. CO2, is it great for the environment? Do we like it?
No.
Not really,
No.
but if we had a choice between carbon dioxide and carbon monoxide, which one would we choose?
Carbon
Dioxide.
dioxide.
Correct, yeah, because the carbon monoxide is far, far, far worse. So carbon dioxide is not ideal, we don't like it, but it's far better than the carbon monoxide that would have otherwise been released. And then nitrogen is harmless, it's in the air in any case. So it goes in as nitrogen, it gets combusted, and then it gets turned back to nitrogen, and it basically comes out the same way that it went in. And then it's basically just part of the air again. So that's pretty harmless. And then for the extended guys, you need to know the equations associated with that. So you have to know these. And I literally just copied and pasted this. This is directly in the syllabus. Cool. So carbon monoxide reacts with oxygen to produce carbon dioxide. In the second one, the monoxides, both of them combine to form the nitrogen and the carbon dioxide. And then the third one, the monoxide is converted to nitrogen and oxygen. Cool. Any questions?
No.
No? So catalytic converters were not always there in the olden days, like before environmental concerns and stuff. Cars didn't have catalytic converters, like literally whatever came out of the exhaust, they pumped into the environment. But obviously with new technology and everything, these things are quite cheap. Does anyone know the metals that they're made out of?
No.
Also, I'll add that to the note as well, but they're actually made of quite expensive metals. They're made of things like rhodium and platinum. So things that are in the same sort of class as gold and silver and those kinds of things. So they're relatively expensive. They're not cheap metals. So a catalytic converter is not a cheap thing. It's not something that you go pick up for $300-400. It costs maybe a couple of thousand. Here all drawings. And then the last thing, another way to protect metals is by galvanizing, which you saw when we talked about metals. So we talked about the galvanizing of metals, and it forms that oxide layer of zinc, which forms a protective coating, and it adheres to the surface, it doesn't peel off. So it's that sacrificial protection. The zinc sacrifices itself for the metal underneath. Any questions?
No, sir.
No? So if you were going to compare galvanizing to painting, what is the advantage of galvanizing over painting? Why is it better to galvanize than to paint?
It won't peel off.
It won't peel off, correct? So once
It will last longer.
it'll last longer, correct? Because it sticks to the surface. And even if there is a scratch, like you'll see in this little diagram here, there's an exposed area. As long as there's enough zinc around, it's going to always react with the zinc first. So as long as it sees zinc, it's going to go for that zinc immediately. Cool. But if that hole got bigger and bigger and bigger, would you say it would help?
No.
No, so you would have to re-galvanize. So very often when you get parts and equipment that are galvanized, they will re-galvanize after a certain period of time. They'll take it to a workshop and they'll have it re-galvanized or resurfaced or whatever you want to call it. Cool. And then what do you think the disadvantage is over galvanizing versus painting?
It's probably more expensive.
Exactly. So galvanizing is probably far more expensive because you're coating it with metal. So you literally have to coat it with zinc. And I don't know what the relative price is, but I'm pretty sure that paint is probably cheaper than zinc for the same amount. Also, advantages and disadvantages. Good to galvanize, but bad because it's expensive. Good to paint because it's cheap, but bad because once you peel off that paint, you expose your surface again. Cool. Any questions? Anything interesting that anyone wants to add? Does anyone have any insights or ideas or something they want to contribute?
So is there something about white rust
Yeah.
of galvanizing? Like
Sure.
If it's like exposed to moisture for a long time,
Sure.
some white rust can form over the zinc.
Are we saying that the rust is forming because the iron is being
It's
because
already been galvanized, but
correct.
if it's like left in moisture for like a really long time,
it might start rusting? Is that what you're saying?
yeah, some white rust. Yeah.
Yeah, the white rust is actually the zinc oxide. The white rust is the zinc that's being constantly oxidized. So when you see something that is, let's take two examples. You have an ungalvanized piece of steel. If that reacts, if that rusts, it's going to form that reddish brown layer. You know what I mean? Have you seen that like reddish brown sort of rusty kind of layer?
Yeah.
Correct. Now you galvanize it and you allow it to, let's call it inverted commas, rust. It's not going to form that reddish brown layer. It's going to form that like whitish layer.
Yeah.
Yeah. And that's the zinc. That's the zinc that's technically inverted commas rusting.
Oh, okay.
Yeah. So the zinc is actually reacting. It's not unreactive. It is actually reacting. And that's also why eventually you would have to re-galvanize because eventually all your zinc would become zinc oxide.
I see.
Cool. So very good question. Somebody else was about to say something? No? Okay,
No.
so that's the end of the lesson. I'm going to update the notes and upload them as soon as possible, as well as C 10.3. And then I'll put the questions and everything as well. But the questions are so straightforward. There's really not a lot. Cool. Happy days. See you guys tomorrow.
Bye, sir.
Bye guys. Be
Thank you.
good. You're welcome.